is going. All right, so we're now dealing with one fixed, one free end. Here's a sample of one fixed and one free end. I have water right here in the tube at this point. That's the fixed end, and then the free end is open. The first harmonic looks like this. I got where my fixed end is, I got a node. Where my free end is, I have an antinode. And that's, the pattern's gonna hold. If there's a fixed end, there's a node there. If it's a free end, there's an antinode there. How many waves is that?
1/4.
Because basically, we're going from node to antinode, we're getting rid of 3/4 of it. And it's indeed a fourth. So that's a fourth of the wavelength is equal to whatever the distance is between the ends. Or the wavelength is just 4 times the length. The next harmonic, the fish.
Wait, sorry. Did you flip the fraction and multiply? Is that how?
From here, if you multiply both sides by 4,
Oh,
they cancel out on this side and it's up to 4 times L.
okay,
Is that good enough?
yes.
Okay. Any other questions? All right, how many waves is this?
It's one and some change.
Is it 1 and 1/4?
Not 1 and 1/4.
1/6.
Is it 1/6?
She didn't
No.
mean it. She didn't mean it.
So basically, we're going from node to the second antinode.
1/8.
It's just 1/2.
So half would be that.
We're not great with math, apparently.
Who said one, like one and 1/2? I don't know, half of it, half of the other one. So one whole one and then a half of it. Well, we know,
3/4.
cause that's not a whole one, cause that right there is a, okay.
That's a whole,
Yeah.
that's a half, that's a
Yeah.
quarter.
Oh,
basically it's a
that's
half
why
and a
you,
quarter.
I was wondering why y'all said that was 1/4, but that whole thing right there is a wave.
Yeah, so that's,
So that's 75% of the wave.
Yeah.
yeah,
What I
so
could come up with. Is that 3/4?
3/4 of a wave, yep.
Okay,
Or 0.75 if you prefer that.
okay.
So the length, oh, sorry, so the wavelength is just 4/3, again, multiplied by the reciprocal to get it over here.
Okay.
Now, just to add to the confusion, because you really don't want any pattern to fit for too long, because then people get complacent.
Well, what you said?
Sir.
This is the third harmonic.
Wait, what?
This is known as the third harmonic.
What about the?
Now
That
doing
was
that
the
in third
third
harmonic.
Yeah, you know,
As he just said,
this is the first harmonic, and then this is the third harmonic. It seems like there should be something here, but there's not, there's no standing wave.
Wait,
The
so-
second harmonic cannot be created in a standing wave.
What's the one on top of it?
Yeah,
That's the first harmonic.
but I thought the other was the.
guys, he said,
Why not?
it's making it more confusing.
There is a reason for this. It delves deeper into the math, and I wanted to spare you that. Now, for a long time, I kept calling this the second harmonic because, hey, it's the one after the first. It really should be the third. If you're looking at old tests, and I refer to the second harmonic for one fixed, one free end, that's what I'm talking about.
Is there, oh, never mind.
The next one would be,
This?
The second,
She didn't.
they're not going that crazy.
I was trying to get you confused, okay?
But in any case, each time works over there, works here, it's gonna work on the next group that we do. We're adding a half wave each time. So from here,
Is that the fifth harmonic?
it'll be the fifth harmonic.
But that's the fifth one, what happened to the fourth one?
The same place the second one went.
Wait a minute.
Technically, the second, here's the thinking behind it. The second harmonic you would add you'd go from node to node, but you can't have a node at the end because it's a free end. So it basically gets skipped.
Oh, copy.
So why don't we just call it the second harmonic?
Why would you?
That would really have made life a lot more convenient.
Why do we still have our harmonics?
They move in harmony.
I was not focused on Now, they decided to resolve the issue of the fact that we skipped the second and the fourth one by using a new word. And they call this the first overtone and the second overtone. That would be the first overtone, the second overtone. So those go in order.
I've heard that in music theory.
So I'll just write it up here. I generally don't make reference to the first or second two overtones. Now, in terms of church music or something like that, or I guess you use music theory, but pipe organs basically have a fixed and a free end.
Bye-bye.
So let's actually make a prediction. Let's see how, it's a physics demonstration, what are the odds that it's gonna work? So in my water tube here, where I got one fixed, one free end, I can adjust the level of water in the tube by adjusting this. The water level here and the water level in the tank are the same. I have the same amount of pressure on both ends, they will equalize. If I lower this, the water in the tube will start to drop also until the water levels are equal. And so I can adjust the length here, in essence, the distance from the node to the antinode, from the node to the antinode, just by adjusting this. The downside is, you might have heard it just then, I tried not to do this, but occasionally there's metal scraping against metal. It's very shrill, and I'm hoping I'm the only one who's really bugged by it, but we'll find out if anyone cringes. So what I'm gonna do is I got a tuning fork right here of a particular frequency, and it's printed on there that's 320 hertz. So my frequency, 320 hertz. And that's based solely upon the fact that it's written on there. Now for some of these I've actually used sound sensors and measured the frequency that way. The ones I've tested are really close to what's actually printed on there. I know that the speed, since I have this thing vibrating back and forth, sending sound waves down the tube and then bouncing back up, but it didn't fall over all the way. I know that the speed of the sound is equal to the frequency times the wavelength. That was the formula we did just before this. The speed of sound is somewhere around 343 meters per second. There's a formula for that based upon temperature, but I'm just gonna go with, this is what I'm gonna consider room temperature. Having done this enough, the temperature is probably just slightly above 20 degrees Celsius, and so the speed's probably slightly above that, but not significantly. So that's the speed of sound, and that's gonna be equal to the frequency of the sound, which is 320 hertz, times the wavelength. So the math problem I'm working with here is 343 is equal to 320 times x, I'm going to use lambda here, but times some unknown. Let me bring this down temporarily. Down. So what is the wavelength that is produced by that?
1.07
Units?
hertz.
Meters per second?
It'll be the unit for wavelength.
And the second syllable there is the key. Wavelength.
Is it meters?
Meters. All right, so the wavelength is 1.07 meters, which means when I flick that, the sound wave has traveled 1.07 meters before the next before the next vibration starts. I know for the first harmonic, the length, this is the length from top to where that is a quarter, go back to the way I had it written before. The length of the air column here, again, from the top to the water, is a quarter of the wavelength. So our prediction is that we need this air column to be a quarter of this. To 675.
Yeah, 1, 2, 6, 7, 5.
Units?
Meters.
I got 0.2679.
Did you round, you had the 1.07, was that, when you
Oh.
just did it, did you use the 1.07 or the real number?
The real number.
Okay, that's,
Okay.
why don't we just say 8? I mean, we can keep taking it out, but we're not gonna be able to get this, be able to identify.
What's the real number that you guys were just talking about?
On that calculator, you,
If you, 343 divided by 320, it's not 1.07 exactly,
Oh, no, it's not. Okay.
Yeah.
Okay,
and so that was the discrepancy.
okay, cool.
All right. So what the claim is that I can start this going and that we should hear the first harmonic when the air column is 24 centimeters. Now, for some reason, and I had a rationalization for it, but it hasn't really panned out, there's a guide right along the side of these. And this tape right here, 0 starts 2 centimeters below the top. So whatever we get on here, we need to make sure we add those 2 centimeters for that gap in the tape. Potentially, we were supposed to saw it off, but we didn't. We just add 2 centimeters. So I would expect since the air column is supposed to be 26.8 centimeters, that when I'm at 24.8 centimeters on this guide right here, that's when we'll hear the harmonic. Now, what would you expect to hear? Because I'm talking about hearing the harmonic, what would you expect to hear differently than just that? And I had a striker, there we go. I'm assuming all of you are young enough to hear that. I can hear it, so I'm assuming anyone else can hear it. What's gonna happen when we're at a harmonic?
Angels.
Angels? That's possible, I'm not quite sure what they sound like, so it's, maybe, that would explain a whole lot.
Are you asking what it's gonna sound like?
Yeah, how do we know when we're actually at the harmonic?
It'll go up a pitch, I think.
If it's going up a pitch, that means the frequency has changed, and the frequency is not gonna change. I suspect potentially your intent was right, or did you actually mean pitch? As in, it would go
It'll
a higher
sound
sound.
Does it have to do with octaves?
That would go along with what Rebecca is saying. It's not, the frequency is not gonna change, the frequency is dictated by this.
Wait, what are we trying to figure out?
When I hit the harmonic, how will that sound different than that?
Will it be louder?
Yes. Because when you get the harmonic, remember we have sound waves going down, hitting the bottom and bouncing back. Right now, they're not in sync. We don't have harmonics, so that we have constructive, destructive interference. We don't have the maximum amount of oscillation here. The bigger this is, the louder we're gonna hear it. And so when we hit a harmonic, we've got, in all the cases, we have an antinode at here, at the open end, and it should be louder. Let's find out if it works. A little bit louder there. Oop, pass it. And on this, it's saying 23.8 centimeters.
Now, I think I heard something like, is that that?
Do it again. That's it right there.
It's pretty freaking cool. I don't know.
It is. You got a little bit louder there. Now we could go for the next one, and let's do it. So that was 20, I saw 23.8 on there, plus the 2 centimeters. So 25.8 centimeters was what we got experimentally. Our prediction was 26.8 centimeters. We're talking a 4% difference there. The next harmonic should happen at 3/4 of the wavelength. Well, we know what the wavelength is, so 3/4 of this. In other words, 3 times that, since that's a quarter, and now we're doing 3/4. So the third harmonic, first overtone, the next harmonic, happens at 0.7,
You said 3?
it's basically 3/4, 0.75 times 1.07.
Oh, sorry. Now I'm going 3/4 times,
Times 1.07.
okay. I got 0.802.
802 meters. Anyone else got the same thing?
I got 0.804, but I used 1.072 meters.
Okay, you went out another one. So in this general range, the difference being 2 millimeters that I'm pretty sure I'm not gonna notice. I'm not gonna be able to tell that.
Wait, so this is the length of the wave?
This is, no, the length of the wave was the 1.07 meters.
Okay. So
This is the length of the air column. This is the length, the distance from the node to antinode.
3/4.
So the open end to the water.
Okay, and to do that, you do the wavelength times the length of the wave?
We did the wavelength times 3/4 to get the length for this next harmonic.
The wavelength times the length.
Because I know that, let's get rid of this stuff. So the next harmonic after the first one, whatever you want to call it, looks something like that. That's 3/4 of a wave. A full wave would therefore, if we just imagine that, the full wave there, that would be the full wave out to here. And that's 1.07 meters. But in this particular case, the distance I want from my fixed end to my free end is 3/4 of that. So this should be 3/4 of the wavelength.
Which equals the distance from the node to the antinode?
Yes.
Okay,
And in this context right here, from the open end to the water.
okay. And is known as, that's not the same as the wave speed?
The wave speed is that, would be a speed itself. The speed of the wave, that's, because it's sound in room that's roughly 20 degrees Celsius, is about 343 meters per second. That's how fast the sound is traveling.
Okay.
Yeah, over in Tech Building, we've actually done some did a little bit of a demonstration of that years ago, where you actually can get at the opposite ends, and you can start to notice that as the mouths move, the sound, there's a delay between the sound getting from them to you. All right, now, because I can get this thing going, but first off, whenever you want to make a tuning fork vibrate, please don't bang metal on metal. You get a really loud sound, but you also start to deteriorate this. So that's why I have the striker here. Now that only lasts a certain amount of time, and so typically I'll get close to where I'm expecting the answer to be before I will let that thing go.
Have a good one, guys.
Alright.
Right up your phones.
See you, Rebecca? Too quiet. It's much subtler. And you can tell clearly it was loudest